Hello and welcome to Night Science Stories. Breathe slowly, let the room grow quiet, and imagine yourself under a sky filled with calm starlight. Picture a faint point of light gliding across the deep background of the constellation of Sagittarius. In the first hours, it looked like any other moving speck. Then the numbers spoke. The path was not the usual ellipse of a bound comet. It was wider and sharper, a curve that never closes. The object was falling from interstellar space, threading the inner system once and then leaving forever. Astronomers call it 3-eye Atlas. It is the third confirmed interstellar visitor seen in our skies, after the elongated wanderer known as Oumuamua and the dusty blue comet discovered by Gennady Borisov. The new object carries the survey name of the system that first noticed it, a network devoted to early warning and to patient nightly searches. It is the kind of visitor that arrives only a few times in a human lifetime. The discovery is simple to state and enormous in meaning. A piece of another planetary system has wandered into ours, and for a short season our telescopes can read its features and its chemistry before it disappears again into the great dark. In the first moments of attention, there is always excitement. For a calm investigation, we must turn that excitement into careful questions. What exactly is this object? How fast is it coming in? Does it shed dust and gas as a comet? Or is it quiet like a bare rock? Does sunlight and heat push on it in subtle ways that change its path? What do the colors of its light say about its surface? And the question that catches every imagination, even as we study it with discipline: could any part of it be artificial? The scientific answer begins with a gentle but firm principle. Extraordinary claims require extraordinary evidence. Most interstellar bodies will be natural comets or natural fragments because nature produces vast numbers of them. That is the sober starting point, and from there we proceed step by step, reading every study like a page in a long book. The discovery itself began in a way that is both modern and quietly romantic. On a routine night, the Atlas survey was sweeping the sky with wide cameras and automated software. The name Atlas here refers to the Asteroid Terrestrial Impact Last Alert System, a set of telescopes built to find small moving objects quickly and to warn us of any that might approach Earth. The software compares new images with old ones and marks faint dots that change position in a manner consistent with a real body rather than a random flash or a passing satellite. On that night, a faint point appeared where no star should be. Follow-up images showed motion against the fixed background. A preliminary orbit was computed and immediately looked unusual. The shape was not closed, it was a hyperbola. That single word carries the whole message. The object is unbound. It is an interstellar traveler. Observatories around the world and above the world quickly turned their attention to refine the path, the speed, and the brightness. The label 3i is not just a nickname. It is a formal recognition by the community that tracks comets and asteroids. The letter I marks an interstellar origin, not a bound orbit. The number is the count of such visitors officially confirmed. First came Oumuamua in the year 2017, then the comet of Borisov in the year 2019, and now this new traveler detected in the year 2025. The word Atlas is a discovery credit. It tells us which system first reported the object. The formal pages of the Minor Planet Center explain the designation in calm, technical language. In the history of astronomy, this is a short list and a meaningful one. The third visitor matters not because of the integer in its name, but because 3 is enough to suggest variety. With 3 examples, we can begin to say that interstellar visitors do not all look the same. Some are dusty and active with gas. Some are dry and quiet. Each is a page torn from a different book of planetary formation. To understand why wide sky surveys like Atlas are good at finding such objects, imagine the sky as a large blackboard and a small dot of chalk sliding across it. A narrow telescope that stares deeply at one tiny patch will miss most moving dots simply because it watches too small an area. A wide survey takes shallower exposures, but covers enormous swaths of sky every clear night. The software then stitches these images into a nightly movie and catches movement as a gentle thread. The Atlas network runs robotic telescopes in different locations to minimize clouds and to add parallax that helps measure distance. It is designed for speed and for coverage. That is why it can notice faint movers that enter quickly from the outer darkness. Other surveys, such as the ones that now feed the Vera Rubin Observatory, will soon expand this capability and transform these rare finds into a more regular stream. But in the year of this discovery, the Atlas network was scanning at the right time with the right cadence, and it deserved the credit it received. To analyze every study on 3I Atlas, we used the gentle discipline of a meta-analysis. Imagine a long table covered with papers, preprints, and observation logs. Our first task was to sort them by method. A group of studies measured the orbit, the position, and the motion, drawing on astrometry from many telescopes. Another group studied the brightness, the color, and the changes over time. A third group pointed spectrographs and listened for faint signatures of gas such as water, carbon monoxide, and carbon dioxide. A fourth group built physical models to see which shapes and spins can match the measured flicker in brightness. A fifth group explored the possibility of small forces that do not come from gravity alone, such as the pressure of sunlight on dust or the recoil effect when gas escapes like a tiny thruster. For each group, we asked the same questions. What is the signal? What is the noise? What is the uncertainty? And is it reported honestly? Can other teams reproduce the result? Then we looked across the groups to see where the lines of evidence meet or diverge. This is slow work, but it is the kind of slowness that brings clarity, which is a fine companion to sleep. The orbit was the first and most important clue. A path is called hyperbolic when the object has more energy than a bound orbit allows. In plain language, the curve bends inward as the object approaches the sun but never closes. After one swing, it opens back out and the traveler departs. This hyperbolic shape can be faked for a local comet if a planet gives it a strong kick. That is why the first tests always check whether Jupiter or another giant could have lent the needed speed. For 3I Atlas, the calculations show that no planet came close enough to supply the extra energy. The object arrived already moving faster than a bound comet can move. The conclusion is firm. It came from outside. Interstellar space sent it, and gravity will send it back. Speed is an attractive detail because it paints a visceral picture in the mind. The new visitor moves through the inner system at a running pace of more than 200,000 kilometers per hour relative to the Sun. Measured in miles per hour, this is well over 100,000. It is quick even by cosmic standards. yet not too quick for telescopes to track. The speed is part of the reason the path is so open. It also increases the energy that sunlight and solar wind can deliver to the surface and to any dust that lifts from it. As the object approached the inner system in late summer, images from large telescopes began to show a subtle tail and a soft, bright head. The broad term for that head is coma. It is a cloud of gas and fine particles expanding around the nucleus under the warmth of the sun. Seeing the coma grow and the new tail lengthen was the moment when many astronomers settled into the idea that this is a cometary body, not a bare rock. That interpretation is not a dismissal. An active comet is a rich laboratory because gas and dust carry chemical signatures from its place of birth. From orbit to brightness we go because the light curve is like a heartbeat. As the comet rotates, different faces and reliefs reflect slightly different amounts of sunlight. If the nucleus is elongated like a potato or a cigar, the light curve will rise and fall with a clear rhythm. If the nucleus tumbles in a complex way, the rhythm can become irregular, like a drum played with an unsteady hand. If dust dominates the light, the curve can smooth because the coma acts like a soft lampshade. Early in the apparition, the light curve of 3I Atlas hinted at variability, but without an obvious period. That is not surprising when a coma is already present. Some teams reported gentle changes that could match a spin of many hours. Others noted that the signal looked like a mix of rotation and evolving activity as jets of gas turned on or off with sunlight. The calm truth is that the light curve at this stage was a blend of nucleus behavior and coma physics, and patience was required to separate the two. The next question is clear. Does the object carry a visible atmosphere of gas and dust, or is it largely bare? High-resolution images from the ground, especially from southern hemisphere telescopes with clear, dry air, began to show a coma that was small at first and then more extended. The tail lengthened in images taken near the end of northern summer, which in the southern hemisphere is late winter. The shape of the tail matched the direction of the solar wind and the pressure of sunlight, which push small dust particles into graceful arcs. Larger particles lag behind and draw a thicker path. When the coma brightened, observers were able to take spectra, prying the light into its delicate colors to search for specific molecules. The first reports that reached the preprint servers and then journals spoke of water and carbon dioxide as likely contributors. The ratios will refine over time, but the basic message is that 3I Atlas behaves like a natural comet. That is a fascinating conclusion because it offers a sample from another star system without needing a spacecraft to go there. It is a small kindness from the galaxy to us, and we should accept it gratefully. A chemical passport is written in faint lines. Water announces itself in the infrared and through the ultraviolet product of hydrogen when sunlight breaks water vapor apart. Carbon monoxide and carbon dioxide leave fingerprints at their own wavelengths. Dust adds a broad slope of color that can make the comet look slightly red or slightly blue depending on particle size. Team by team, the reports assembled a picture. Some suggested that the comet carries a larger fraction of carbon dioxide than a typical short-period comet from our own family. That would make sense for an object formed in the very cold outer reaches of another protoplanetary disk. Others cautioned that sensitivity limits make firm ratios difficult this early in the approach, since the comet is still far from the Sun compared with our inner planets. A patient truth has to be said softly here. Much of what we will learn about composition will arrive after the comet has rounded the Sun and brightened further. In late autumn, the geometry will place it behind the Sun from Earth's point of view, so the best new measurements may arrive when it emerges again into pre-dawn skies. The comet will remain far from Earth and poses no threat at all. Our role is to watch and to learn while it passes. The orbit and speed also let us predict the schedule of the encounter. The closest point to the Sun will occur around the final days of October of this year, at a distance a little inside the orbit of Mars. The closest approach to Earth will arrive weeks later in December, still far away, well over 150 million miles. The exposure will be brief and safe. The window for deep spectra will be early evening or pre-dawn, depending on the month and the latitude of the observatory. Large telescopes with infrared instruments and sensitive cameras will carry most of the load, though small telescopes can continue to monitor brightness and look for outbursts. Space-based observatories may deliver the best insights into the gases because Earth's air absorbs many of the lines we need to see. The Gemini South Telescope has already delivered striking images showing the tail growing. Other facilities are cued to watch when geometry and weather allow. One recurring question is whether non-gravitational forces alter the path in a measurable way. When sunlight pushes on dust, the pressure adds a little acceleration. When gas jets away from the nucleus, the recoil gives a tiny shove. For a small body, these effects can be seen as a slow drift from the trajectory predicted by gravity alone. Oumuamua showed such a drift, and that fueled many speculations about its nature. For 3I Atlas, the early orbit refinements have been consistent with ordinary cometary forces as activity increases near the Sun. The magnitude of any extra acceleration so far is modest and points away from the Sun, which fits the idea of gas flowing from a warm surface. This is not a disappointing result. It is a useful one. It lets us place 3I Atlas in the natural family of comets without closing the door to interesting physics in the details of how dust is lifted and shaped by heat. When we compare all 3 interstellar visitors known to date, a calm pattern appears. The first, Oumuamua, was small, dry and strange, with a brightness curve that suggested an unusual shape and a push that did not fit simple dust models. The second, the comet of Borisov, looked like a more conventional comet, dusty and active, with a composition that resembled the cold building blocks of our outer system. The third, 3I Atlas, seems to lean toward the cometary side. It carries gas and dust. Its path is cleanly interstellar, with no planetary kick within reach. The differences among the 3 tell us that planet-forming disks around other stars generate a wide menu of fragments. Some may be compact and dense, others may be fragile and rich in ices. Over time, we will see many more, and the distribution of their types will become a statistic rather than a set of anecdotes. For now, we hold 3 notes, and we can already hear the start of a melody. Light curves deserve a deeper look because they carry quiet hints about shape. A smooth, low-amplitude curve suggests a rounder nucleus or a coma-dominated appearance. A large amplitude and regular period suggests an elongated body rotating like a baton. If the curve is irregular or shows multiple periods, the body may be in a complex spin state, sometimes called tumbling. The earliest analyses of 3I Atlas speak of low amplitude variability and of the influence of the coma that fits the images that show a persistent growing cloud. As the object recedes after perihelion and the coma thins, we may see the nucleus more clearly and estimate its size and rotation with better confidence. Until then, the best practice is to model the light using a range of plausible shapes and to ask which shapes are not compatible with the data, instead of insisting on a single favored geometry. The images that separate coma from nucleus rely on good seeing and careful processing. Some teams use deconvolution techniques to strip away the blur of the atmosphere and reveal the inner structure of the coma. Others fit the light profile with a combination of a point source for the nucleus and a set of power laws for the coma brightness. The goal is to decide whether there is a jet, a fan, or a symmetric cloud. A jet can tell us about the orientation of the spin axis. A fan can reveal the places on the surface where heat reaches volatile pockets. A symmetric cloud is the simplest case and suggests widespread, gentle activity. In late summer, the consensus leaned toward a small but genuine coma with a tail aligned in the expected way. The earlier spectra hinted that both water and carbon dioxide were present. Those molecules are the workhorses of cometary activity at the distances where 3I Atlas travels. A natural next step is to ask where in the galaxy such an object may have begun its life. The direction of arrival points roughly toward the inner Milky Way. That does not mean it came from the very center. It simply reflects the fact that there is more galaxy in that direction than in the opposite one. The chemistry we eventually measure will say more. A high fraction of carbon dioxide and carbon monoxide would suggest an origin in a very cold zone of a distant disk, perhaps far beyond the ice lines where those gases freeze. The dust grain sizes will also help. Fine dust points to fragile surface layers being lifted easily. Coarser dust suggests more consolidated material. The truth may be mixed, as comets are layered by the history of their formation and by later processing. Nature rarely gives a single simple answer. There is also the question of size. Early estimates from brightness and from the activity level suggest a nucleus that could be several kilometers across, perhaps on the order of 10 kilometers, though such estimates carry wide error bars until the coma thins or until thermal measurements arrive. If later data confirm a multi-kilometer scale, that would place 3I Atlas comfortably in the range of medium comets. The mass, the porosity, and the cohesion are unknowns that models will explore by asking how much gas is needed to drive the observed tail and how dust grains accelerate in the flow. The phrase extremely old has appeared in a few articles because an interstellar comet can wander for hundreds of millions or billions of years between stars. If this body formed in a disk older than our Sun and was ejected long ago, it has traveled through the galactic tide for a very long time. That age is not written on its surface in numerals, but it is hinted in the simple fact of interstellar arrival. Some writers have wondered aloud if such an object could conceal technology. The healthy way to treat that possibility is straightforward. Keep open eyes, look for anomalies that resist natural explanations, demand independent confirmation. So far, everything about 3I Atlas fits the pattern of a natural comet. The tail grows as sunlight increases, the coma carries common molecules, the path curves as gravity dictates, with only small extra pushes from normal outgassing. None of this proves that technology is impossible in principle. It simply says there is no need to invoke it here. Our curiosity is satisfied by the beauty of natural processes, which is their own quiet kind of wonder. Now, let us fold the science back into the rhythm of a bedtime documentary and imagine the encounter as a slow dance. The object approaches the orbit of Mars and then turns inward a little more, not enough to threaten any planet, just enough to feel the warmth and to breathe a little. In late October, it rounds the corner and begins to recede. In December, it is at its nearest to Earth, still a long and safe distance, a dark traveller trailing a thin ribbon of dust. It slides away toward the outer planets and then into the background of stars, bound for the spaces between suns where the light is soft and rare. The data remain behind on our servers and in our journals. The ideas circulate in our minds and in our classrooms. The object itself carries on quietly, which is perhaps the best way to end such a visit. Before we rest, it can be calming to summarize what a full reading of all the early studies actually says. The object is interstellar beyond reasonable doubt because its path is too open to be explained by any planetary kick, and because its speed is too high for a bound origin. It behaves like a natural comet with a growing coma and a tail that lengthens under solar heating. Preliminary spectra point to water and carbon dioxide as drivers of activity, with dust grains that create a soft blue-white glow in images. The light curve suggests rotation but is mixed with activity, which makes precise periods difficult for now. Non-gravitational forces are present at a level consistent with gas flow and sunlight pressure. The perihelion distance and the timing ensure that Earth remains safe and that the best observing windows will be before and after the bright but short solar conjunction. The variety among the 3 interstellar visitors so far argues that planetary systems eject many kinds of bodies, from dry shards to dusty snowballs. Future surveys will find more, and one day a spacecraft may be designed to wait in a ready orbit, the way a patient heron waits in a quiet cove, able to launch and meet the next traveller on short notice. For a moment, let us place 3I Atlas beside a quiet pond in the mind. The pond is the solar system, leaves are the planets, small insects are our usual comets and asteroids, darting around in familiar loops. From time to time a dragonfly passes through, cutting a straight line that does not circle back. It comes from another pond. It drinks a little sun, shows us the shimmer on its wings, and then goes. We do not need to invent a story about engineers shaping the dragonfly. Its beauty is complete as a natural thing. We only need to watch carefully, write clearly, and hold our conclusions with a gentle grip that can tighten or relax as new data arrive. If you are drifting toward sleep, that is welcome. You have walked through discovery and classification, through orbits and light curves, through gas lines written in color, and through gentle questions about pressure and drift. You have heard what the first studies show and what they do not yet show. You have seen how a scientific community moves as one body with many hands, refining a path, sharing images, and challenging claims that rise too fast. The truth, as it stands tonight, is calm. 3I Atlas is a natural interstellar comet, the third of its kind that we have seen. It offers a glimpse of another system's cold building blocks. It travels quickly and safely past the Sun and will be gone again before another season passes. The lessons it carries will remain. Thank you for listening with a quiet mind. May the soft arc of this visitor and the patient work of those who study it carry you gently into rest. When you close your eyes, picture a blue-white comma of light on a black canvas, and the smallest drift of dust marking its passage. Somewhere in the distance, beyond the glow of our star, there are other suns and other disks and other comets wandering between them. They have been traveling for a very long time. Tonight, one of them shared a few secrets with us, and that is enough. The smallest forces can steer the greatest journeys. When we follow the path of 3I Atlas with a patient pencil, gravity describes the broad curve, but tiny pushes write the delicate flourishes along the margin. Astronomers group these gentle nudges under a single calm phrase. They are non-gravitational accelerations. Sunlight exerts pressure on every grain of dust and on the body itself. Gas escaping from warm patches behaves like a miniature thruster. Even heat that the surface absorbs in daylight and releases at night can produce a thermal recoil that shifts the course by a whisper. The Yarkovsky effect, named long ago for the person who explained it, is one such thermal whisper. None of these forces shout. They add up over many days and weeks, and they leave a signature that careful orbit fits can hear. To measure such small pushes with confidence, observers do not rely on one telescope and one night. They blend positions recorded from many longitudes and many apertures. Each measurement carries its own blur from air and optics, but together they form a net that can catch a deviation as small as a few arcseconds over many weeks. The method is humble. Predict the path using gravity alone, compare the prediction to fresh positions, and ask if there is a consistent drift. If the comet is exhaling gas mostly from the sunlit side, the extra acceleration often points away from the sun. If dust dominates, the pressure of light can make the drift depend on the amount and size of grains. When the coma waxes and wanes with the day and the night on the turning nucleus, the direction of the push can slowly rotate. The result is a smooth but real departure from a purely gravitational track. For 3I Atlas, the early reports suggest a modest non-gravitational term that behaves like ordinary outgassing. In a calm voice, the orbit is interstellar by birth, and the small extra shove is the natural breath of a warming comet. Shape and internal structure sit just behind these forces because a body responds to sunlight and to its own spin according to its figure and its density. Imagine 3 archetypes. The first is an elongated shard, perhaps a tough remnant of a larger object, turning like a baton in the sunlight. The second is a compact monolith, closer to a sphere, whose light curve would change only gently as it rotates. The third is a rubble cluster, a porous assembly of pieces that behave collectively like a single body, but scatter light and hold heat in a very different way than a solid stone. Which one is 3I Atlas? The early brightness data point toward a small amplitude, light curve that is already dominated by a coma. That tends to hide the nucleus and suppress strong brightness swings. The indirect clues therefore come from how the coma brightens, from how jets form, and from how stable the rotation seems to be. A fragile rubble cluster often has low bulk density. When sunlight warms such a surface, gas can percolate through pores and carry dust from a broad area. The coma looks smooth and symmetric. A monolithic body with a few isolated volatile patches might instead show narrow fans or jets that turn on and off as the nucleus spins. An elongated shard can produce a longer period in the light curve and can focus thermal stresses into its ends, where fractures open easily. Each scenario leaves different hints in the way the coma expands and in the way the non-gravitational push evolves with time. Models built to match the present appearance of 3I Atlas favor a nucleus that is not extreme in shape and that carries enough volatile material to speak with a soft voice rather than a sharp jet. This is an inference to carry gently because the coma conceals the core. As the visitor recedes and the coma thins, the hidden figure may show itself more clearly. All of these pictures live inside thermal models because heat is the master of tempo for a comet. Sunlight falls on the surface and is absorbed in the topmost grains. Some fraction is reflected to space. The rest diffuses inward as a slow wave of warmth, whose depth depends on how the material conducts heat and on how fast the nucleus turns. If a crust of dust blankets the ice, it acts like a thermal mantle. Under this blanket, ices can remain cold even when the surface warms at noon. Gas then escapes from points where cracks punch through the crust or where the blanket is thin. The balance between absorbed sunlight, radiated heat, and latent heat carried away by vapor sets the rate of activity. Because 3I Atlas travels within a range where water can sublimate and where carbon dioxide can gas off even more easily, both molecules may play roles at different distances from the Sun. When the comet is far, carbon dioxide and carbon monoxide can begin to stir. Closer in, water becomes the main voice. Thermal modeling also connects directly to the small orbital pushes. When gas flows from one sector of the nucleus during the day, it produces a recoil that points in a specific direction. If the nucleus rotates quickly, the direction averages around a circle and the net push is smaller. If the rotation is slower, the push can be more coherent and more easily seen in the orbit. In a few cases, thermal re-emission itself produces a small net force, because a warm afternoon side radiates more thermal photons than the cool morning side, and those photons carry momentum. For a dusty comet, gas recoil tends to dominate. For a quiet stone in an asteroid belt, thermal recoil can be the main actor. 3I Atlas lives in the first category. The gas is the language. The orbit is the transcript. Any new interstellar visitor invites a comparison with the first one we ever saw. Oumuamua entered quietly, brightened only a little, and left no clear coma behind. Its brightness changed by many magnitudes over a single rotation, which suggested a very elongated figure or a very flattened sheet-like form. It showed a small non-gravitational acceleration, which stirred debate because some of the usual cometary explanations looked strained if the body was so dry. The object pushed its way into a thicket of ideas. Was it a shard of a planet crust, a fluffy aggregate, a hydrogen-rich iceberg, or a thin sail-like sheet? Years later, the consensus remains that it was natural, but the details are still argued with care because the data were sparse and the geometry was not kind to observers. 3I Atlas is kinder. It grows a coma you can see. It gives spectra that carry the smell of common ices. It behaves like a comet, and thus does not need exotic material to explain the small extra push. Where Oumuamua left us with a posture of puzzled gratitude, 3I Atlas offers steady facts and a calm outline. The second visitor, the comet of Borisov, looked familiar from the beginning. It carried a broad coma and grew dust tails that caught sunlight in familiar ways. Its spectrum looked like the spectra of our cold comets from the outer solar neighborhood. The message there was warm. Planet building beyond our sun produces frozen bodies that are cousins to our own. 3I Atlas seems to fall nearer to the Borisov side of the family. It is active, dusty, and rich in ordinary volatiles, yet it is not a mere twin. The ratio of carbon dioxide to water may differ, the size of dust grains and the structure of those grains may differ. The timing of activity as a function of distance appears to follow its own curve. That is the charm of interstellar sampling. Even when the recipe is traditional, every kitchen makes a soup with its own spice. To refine orbits and to build better light curves, astronomers practice a quiet art with a lovely name. They search for precovery images. A precovery is a photograph taken before the official discovery, often by a different survey with a different purpose, in which the object happens to appear faintly. Modern sky surveys collect enormous catalogues of images night after night. Software can sift these older frames and ask whether a moving object would have been captured given the later orbit and the expected brightness. If a faint speck appears in the right place with the right motion, it becomes a precious early dot on the timeline. Each precovery extends the arc of observations backward, reduces uncertainty, and pins down the path. It can also reveal whether the object brightened more quickly or more slowly than expected, which hints at how easily it releases gas and dust. For 3I Atlas, teams working with archives have already begun to add these early points, quietly tightening the knots in the orbit and giving context to the later flare of activity. Discovery itself is entwined with selection effects. A survey finds what it is built to find, and it misses what it is not tuned to see. Interstellar objects that are dusty and active are easier to notice because they are brighter than bare rocks of the same size. Bodies that pass close to the sun or close to Earth will brighten more and thus cross the detection threshold. Slow movers linger in the search fields longer than fast movers at the same brightness. The cadence of a survey matters. If the same patch of sky is visited often, motion is easier to confirm. If the exposures are shallow, only the brightest comets appear. These filters do not change the number of visitors, but they change the sample we see. From 3 known visitors, we would be unwise to generalize too far, yet we can already say that purely inert interstellar pebbles likely pass often without notice, while active comets announce themselves. In the coming years, surveys with deeper exposures and broader skies will push the thresholds down and bring quieter bodies into view. Light that scatters from dust carries more than color. It carries memory of particle size and shape. Polarimetry is the tool that reads this memory. When sunlight scatters off a grain, the electric field can become preferentially aligned in one plane. The degree of this alignment, called polarization, depends on the angle between the sun, the dust, and the observer, and on the properties of the grain. fluffy aggregates of tiny monomers produce a different polarization curve than compact spheres. Grains with ice coatings differ from dry grains. By measuring polarization at several angles and wavelengths, observers can infer whether the coma is built of fragile clumps or sturdier pieces. 3. I-Atlas appears to produce a polarization pattern consistent with moderately porous aggregates, a gentle way of saying that its dust is not made of perfect spheres, which no one expected, but of irregular clusters that can break in sunlight and smooth in the coma. The color of the coma also matters. Many comets show a slight red slope in the visible spectrum, which suggests a dominance of larger grains. A blue slope can hint at finer dust. Early color measures for 3 I-Atlas lean toward a neutral to slightly red tone which sits comfortably within the comet family. The tail is not a single brush stroke. It is a family of strokes laid one over another by grains of different size and different birth times. If you imagine releasing sand and powder into a gentle breeze, the powder will fly farther, the sand will fall closer, and the pattern on the ground will reveal when each handful was thrown. Models of comet tails use that same idea. They compute the path of grains pushed by sunlight with strength inversely proportional to size, and they then overlay curves that connect grains released at the same time or with the same ratio of light pressure to gravity. By tuning the distribution of sizes and the rate of release, the simulated tail can be matched to the observed one. In 3 I-Atlas, the tail grows in a direction set by both the orbital motion and the solar wind, with a smooth, broad profile rather than a narrow, spiky one. That argues for steady activity from a significant fraction of the surface, not just from a single jet. The absence of strong striations suggests that very large chunks are rare, while the overall brightness indicates that fine to moderate grains are plentiful. Tail morphology entwines with origin because the ease with which grains lift depends on how they are cemented. In regions of a nucleus that have been baked by past perihelion passages, a crust of sintered dust can form that resists erosion until gas pressure builds strongly. In fresh terrain, the bond can be weak and dust lifts with little delay. If 3 I-Atlas is a newcomer to the inner zone after eons of deep cold, a more even response to sunlight across its face would make sense. The models of its tail encourage that peaceful interpretation. A comet that wakes without violent outbursts is a good target for precise measurements because the slow changes are easier to track. From tails and comas, we turn one last time to beginnings. How do such bodies start their long pilgrimage? In young systems with forming planets, giant worlds interact with belts of small, icy objects. The slow exchange of gravity between a large planet and a minor body can pump energy into the smaller orbit and sling it outward. Repeated nudges can move a comet from a stable circle into an escape path. Close encounters between giants can stir entire belts and eject swarms of fragments. Collisions among young planetesimals can create shards with odd shapes that later encounter a giant and are sent into the dark between stars. In binary star systems, the complex dance of two suns can destabilize debris zones and send objects through gravitational gates that lead outward forever. Even the birth environment matters. Many stars are born in clusters where neighbors pass close. A neighboring star can strip away the outermost bodies from a young system and set them roaming the wider galaxy. Each scenario leaves hints in chemistry and texture. A body ejected early from a cold outer nursery may be rich in carbon monoxide and carbon dioxide ice and may carry very fine primitive dust. A body ejected later after it has warmed and cooled several times on bound orbits may carry a sturdier crust and show delayed activity. If collisions made it a long, thin fragment, its rotation can be complex unless gas drag or internal damping has calmed it. 3i Atlas so far looks like a gentle child of a cold nursery, lightly processed, willing to tell its story in water vapor, carbon dioxide, and soft dust, rather than in violent outbursts. It drifted for a span of time that we measure in hundreds of millions of years, perhaps in billions, bathed in starlight, faint as breath, until one day the geometry lined up and it met our sun. For a short chapter, we are able to read it, to compare it to the two earlier visitors, and to let the quiet conclusions settle in our minds. When all these threads are woven together, the pattern is steady. Non-gravitational forces are present and ordinary. The shape and density are likely unextreme, with a nucleus that is neither a needle nor a sheet, and with porosity that allows gas to seep and dust to lift smoothly. Thermal physics plays the central role in the timing. The comparisons with the first visitor and with the comet of Borisov frame 3i Atlas in a natural family. Archive searches refine the orbit and the light history. Selection effects explain why we tend to meet active travelers first. Polarimetry and color speak of fluffy grains rather than glass beads. Tail models whisper of steady breathing rather than spasms. And the birth stories in other systems give us a generous set of paths by which such a fragment can be set free. It is a good place to rest in the narrative. The facts are enough. The wonder comes not from speculation, but from the simple idea that, now and then, the galaxy reaches across the darkness and places a visiting pebble in our light. The deep between stars is not a void that erases, it is a slow freezer that preserves. A small body that is pushed out of its native system enters a journey measured in hundreds of millions of years, and perhaps in billions of years. Its ices grow quiet, volatile molecules settle into deeper pores and become stable in the cold. Cosmic rays and charged particles slowly brown the outer grains and build a thin crust. Dust on the surface sinters. Pores seal and reopen over ages. The object cools toward the background of the galaxy. Yet the interior is not entirely silent. Heat from the long-ago formation is gone, but the slow dance of phase changes remains. Amorphous water ice can trap other gases. When it is later warmed, it can turn crystalline and release what it held. This is one of the keys to why a traveler that has slept for eons can awaken gently when it drifts into the sunlight of our star. As 3i Atlas approached the inner kingdom of our system, different ices began to stir at different distances. Carbon monoxide and carbon dioxide can whisper from a very cold surface far from the sun. Water waits longer. When sunlight finally warms the skin above its threshold, tiny reservoirs open, and the comet breathes in earnest. The order of awakening matters. Early outgassing from carbon monoxide and carbon dioxide can lift dust from a large area and build a smooth coma even before water is free to flow. Later, as water takes over, the flow can change direction with the daily cycle on the rotating nucleus. These layers of activity are why the tail is not a single, simple plume. It is a history written in particles of many sizes, launched at many times, and sorted by the steady pressure of light. Between stars, the object learned endurance. Near the sun, it learns speed. Dust grains that were welded to each other by cold are coaxed apart by vibration and by the gentle push of gas. Minute pebbles slide from slopes to hollows. Fractures deepen in the afternoon as the warm side expands. They tighten at night as the shadowed side shrinks. No single moment is dramatic. The sum is, the coma grows, the tail lengthens. Spectra gather faint lines from water and carbon dioxide and the bits of dust that carry complex hydrocarbons. It is a natural ritual. The visitor warms. We read its chemistry and its physics at the pace that the object sets. Because we have seen only a few interstellar wanderers, a common question comes easily in a quiet voice. How many more are coming? The answer is changing as our instruments change. Wide field surveys scan the sky with a rhythm our grandparents could not imagine. The most ambitious of them, the Vera Rubin Observatory that will conduct the legacy survey of space and time, is designed to take a fresh, deep movie of the sky again and again. It will watch almost the whole dome every few nights. It will notice faint, slow movers that earlier programs would have missed, and it will also detect fast visitors that announce themselves for only a short time. Forecasts differ because they depend on assumptions about how many objects drift between stars and how bright they become near the sun. Even with cautious numbers, the phrase every few years becomes plausible for the detection of interstellar guests. Optimistic counts hint at several per year. Whether the flow is a trickle or a stream, the meaning is the same. The surprises will not stop at 3. The sample will grow large enough to show families and outliers, and it will turn anecdotes into statistics. With more visitors will come an old dream made new. Could we ever fly to meet one in person? There are 2 philosophies for such an encounter. The first is the sprint that begins only after discovery. An alert arrives. A spacecraft is prepared. It launches on a path that uses gravity from Earth and perhaps from Venus or from Jupiter to bend and speed its way toward the traveler. The second is a patient wait. A spacecraft sits quietly at the second Sun-Earth Lagrange point or in a loose solar orbit, always fueled, always ready. When a new object is found, this craft makes a short burn and falls into a crossing path. The second strategy is kinder to timelines. The first can deliver larger payloads if the geometry is friendly. Both benefit from advances that are already at hand. Ion engines sip propellant and push for months with a steady electric breath. They are ideal for precise path shaping and for fine approach work near a small body. Solar sails do not drink propellant at all. They spread a thin reflective sheet and borrow momentum from light itself. A sail is excellent for patient station keeping and for graceful turns that waste no fuel, though sails are delicate if a mission needs to dive close to the sun for speed. Chemical engines still shine when a fast injection is required at launch or during a close planetary flyby. And then there are gravity assists, the quiet gifts of orbital mechanics. A swing by Venus can lean a path inward. A bend past Earth can tweak timing. A deep pass near Jupiter can fling a craft onto a high-energy arc. Architects of missions mix these tools like an artist mixes colors, searching for routes that meet the object while there is still time to measure. Meeting a traveler is one thing. Measuring it is another. Cameras will give shapes and textures if we can come close. Spectrometers will read gas and dust. A dust analyzer can weigh a grain and tell whether it is fragile or compact. A magnetometer can look for magnetic fields in the coma. A plasma instrument can feel the touch of the solar wind on the new atmosphere. The dream extends to sampling, but the cost of bringing bits home from an unbound visitor is large. For the near term, flying laboratories that taste the flow are a wise middle ground. On Earth, we have another instrument that seems at first to be perfect for strangers. Planetary radar can map near-Earth asteroids with stunning detail and can measure distance and velocity with precision. Yet radar has limits that matter for interstellar comets. The echo is weak when an object is small, far, and wrapped in a hazy coma that scatters the radio waves. The signal-to-noise ratio falls quickly with distance. The sweet spot for radar is close approach. Interstellar visitors spend their brief time in the inner system far from Earth. For 3I Atlas, the geometry is safe and the distance is wide. That is good news for our planet and disappointing news for radar enthusiasts. Other options remain. Infrared telescopes can measure thermal glow and reveal the size of the nucleus even through a modest coma. Spectrographs on large telescopes can separate blended lines and pull out the signatures of specific molecules through the breathing of Earth's air. Polarimeters can read dust structure. Each technique takes a piece of the puzzle. Any traveler that passes within our notice inevitably raises the question of safety. The scenes of cinema are dramatic, but the facts for 3I Atlas are clear. The path is wide. The closest pass to Earth is measured in many tens of millions of kilometers. No fragment large enough to matter is aimed at us. Even the fine dust that creates meteor showers is unlikely because the path does not intersect our orbit and because the tail is modest. The real risk in such seasons is a very human one. It is the lever of attention. If a comet is bright and the words are careless, rumors spread faster than the object moves. The answer is to speak plainly and calmly. This is a natural comet. Its path is open. Its distance is large. Its danger is none. Misinformation loves speed and simplicity. Science loves patience and clarity. A few recurring myths are easy to set aside. Some say that the word interstellar is a guess. It is not. The shape of the orbit and the speed near the Sun define the origin. An open hyperbola with a large excess speed is not made by a hidden planet. It is the mark of arrival from the outside. Some say that activity without a visible coma means technology. It does not. A small coma can be hard to see in poor seeing or with modest instruments. A gentle outgassing can push a body enough to see in careful orbit fits without lighting a dramatic cloud. Some say that a color is unnatural. Colors of comets vary with dust size, with composition, and with the angle of observation. The palette of nature is wider than our intuition. The cure for these myths is simple. Show the data, show the uncertainties, repeat measurements, invite independent teams to check. The road from first claim to consensus in astronomy is well worn. A team posts a preprint. The community reads quickly and writes politely if something seems amiss. Observers around the world test the claim with their own telescopes. Reviewers at journals ask for clarifications and for careful handling of error bars. Numbers are updated as new nights add to the arc. The Minor Planet Center refines the orbit solution and assigns official designations. Large facilities allocate time when the geometry becomes favorable. In a few months, the blurry outline fills in. The more dramatic ideas either win support from new evidence or they fade gently as the patient explanation proves sufficient. In this process, nothing is lost. Even a wrong path can teach by showing where the data cannot be stretched. This is how the field moves together, not in a straight line, but in a narrowing spiral toward a shared picture. In that picture, astrometry holds a special place. A single night of precise positions added at the right time can change everything downstream. When an object is new, the uncertainty cloud around its path is large. Observations from widely separated longitudes and latitudes collapse that cloud. A few very accurate measurements from a large telescope with stable tracking can remove biases and reveal a subtle non-gravitational drift. Later, when the object is faint and distant, a single detection can anchor the outbound leg and prevent the uncertainty from ballooning. Experienced observers know to watch the geometry and to strike when the angle between the Sun and the object and the Earth makes the leverage best. They also know to report honestly when the star field is crowded or the air is unsteady. Good astrometry is a craft as much as a measurement. From a single precise position to a single dust grain, the scale changes, but the lesson is similar. One grain can speak volumes about its birth if its polarization signature looks like a fragile cluster of tiny subgrains. We infer gentle growth in a cold environment where collisions are slow and sticky. If the grain reflects light with a neutral color and shows a glassy spectrum in the infrared, we infer silicates like those in primitive meteorites. If organics coat the surface, we read a history of radiation chemistry in the dark. The distribution of grain sizes in the coma tells us how easily the surface releases material. A dominance of very fine grains tells of a weak crust and low cohesion. A larger fraction of coarse grains hints at stronger bonds and deeper fractures. The gas that carries the dust provides the other half of the story. A relatively high ratio of carbon dioxide to water suggests a formation beyond a distant ice line in a cold disk. A dominance of water with only a whisper of carbon monoxide suggests a region closer in. The gentle truth is that nature rarely gives a pure case. Mixed histories are common. The art is to separate the threads without tearing them. With these tools and with this calm method, the third visitor becomes more than a news item. It becomes a teacher. It confirms that other stars build the same sorts of icy planetesimals that our own star built. It reminds us that gravity is a patient engine that can eject small bodies into the space between suns with no need for drama. It shows that comets that have wandered for ages still wake when the warm breath of a star touches them. It invites us to imagine a future in which we are ready with a quiet spacecraft in a quiet orbit, able to match pace with the next traveler and to taste its breath up close. And it whispers a humbler lesson. Even an object that will never return can reward careful work with understanding that does not fade. If your mind is drifting now, let it drift through a few images one more time. Dust grains that slept for ages release as a soft fog. Gas from deep pores finds a crack, hisses into space, and nudges the nucleus by a fraction too small to see in a single night and large enough to measure over weeks. A survey takes a picture, then another, and the moving dot reveals itself by its patience. A team finds an older image and adds a small point on the page, and the orbit sharpens. A radio dish listens for an echo and hears only the quiet wash of space because the visitor is too far and too soft. A spectrograph reads a thin line from water and another from carbon dioxide. A polarimeter reports that the dust is fluffy rather than smooth. An ephemeris is updated and the small drift is acknowledged as the exhale of a natural comet. In a year, the traveller will be dim and the papers will be filed. In a decade, we will have a handful more and a clearer map of what other systems spill into the dark. In a human lifetime, we may have a craft that meets one not with a shout, but with a whisper. A single dust grain can hold a biography of a distant world. Under a microscope, a cometary grain is rarely a neat sphere. It is more often a fragile cluster of smaller particles welded by gentle collisions and by frost. If the grain contains tiny crystals of silicate, it whispers that it once felt strong warmth near a young star before it was carried outward by gas flows. If it contains abundant amorphous material and stubborn ices, it points to birth in a deep, cold nursery far from any heat. The grain's color tells of the organic films that radiation paints over ages. Its porosity tells of gentle assembly in a low-gravity dawn where impacts were more like embraces than blows. A single grain, therefore, encodes the traffic pattern of a protoplanetary disk. Crystals near the furnace moved outward. Frost from the far dark moved inward. The two mingled and became the raw material of worlds. When 3I Atlas releases such grains, even our simple measurements of color, polarization, and infrared glow let us test that picture. If we see crystalline silicates together with very cold, loving volatiles, we learn that mixing in distant disks is vigorous. If we see only primitive glassy material with heavy organic mantles, we learn that some disks shelter their outer regions from inner heat and light. From one grain, we infer the busy lanes of an infant system and, by extension, the possible roads that planets took as they migrated. Migration begins with gravity in conversation with motion. Picture a small icy body wandering near a giant planet. It arrives on a quiet ellipse. The giant's gravity gives it a swift handshake. Energy is exchanged. The small body departs on a new path. If the timing is just so, repeated handshakes occur. Each encounter stretches the ellipse. After enough stretching, the ellipse opens into a hyperbola. The body is ejected and becomes a drifter between stars. In other stories, a period of orbital resonance pumps the eccentricity upward until a single close pass flips the sign of the binding energy. In still other stories, a close partner star tilts the orbits and drives them to extremes through cycles that astronomers call Kozai-like oscillations. A crowded birth cluster adds another path. A passing sun adds a long, gentle tug that frees outer debris from a newborn system. The mechanics are diverse, but the outcome is the same. Small bodies are plentiful, and a small fraction of them is always being sent outward forever. When we see 3 different interstellar visitors in less than a single decade, it is a reminder that ejection is not a rare accident. It is a normal breath of planetary formation. How many such drifters live in the space near our Sun? The honest answer carries a wide margin. Estimates range from surprisingly sparse to surprisingly crowded because they depend on how big the bodies are, how bright they become near the Sun, and how efficiently young systems fling them away. What we can say calmly is that the number is non-zero and that the sky is large. Wide surveys have already turned a rarity into a repeating event, with the Vera Rubin survey preparing to make a deep movie of the heavens. The cadence of discovery will quicken. A conservative forecast points to a new interstellar visitor every several years. An optimistic forecast imagines several per year. Either way, the statistics will harden. We will know how often comets like Borisov appear and how often dry shards like Oumuamua appear. We will measure the share of wanderers that arrive as gentle, active comets like 3I Atlas. In a few decades, the phrase interstellar visitor will feel less like a headline and more like a chapter title in a steady atlas of the sky. After its brief hello, our visitor continues outward on a path that is simple to describe and beautiful to picture. It leaves behind a faint ribbon of dust and a trail of numbers in ephemeris tables. Its speed, far from the sun, settles to a steady surplus above the escape value, a surplus of several tens of kilometers per second. Relative to the gentle swirl of nearby stars called the local standard of rest, the direction is unremarkable. That is its own quiet lesson. There is no single preferred stream. Interstellar space is populated by travelers launched at many times from many cradles. 3I Atlas becomes one more point in that slow rain of comets drifting on galactic orbits. It passes beyond the heliosphere into the thinner medium where the wind of our star yields to the broader breeze of the galaxy. Its surface will again brown under radiation. Its pores will again freeze. It will carry the memory of our sunlight for a distance we can barely imagine, and then it will fall into another star's influence or perhaps never be noticed again. That sense of variety returns whenever we compare visitors. Why are interstellar wanderers so unlike one another? The first reason is birth. Disks around young stars differ in mass, in temperature, in the strength of ultraviolet light, and in the rate at which they feed gas onto their suns. Some disks host early giant planets that stir their neighborhoods. Others stay calmer. The second reason is architecture. A system with a massive giant close to the star will eject debris differently than a system with distant giants on gentle circles. The third reason is weathering. Between stars, the radiation field slowly changes surfaces in ways that depend on the starting composition and on the total travel time. A fragment that has made several close passes by suns will be crusted and dry. A fragment that slept in the deep dark will awaken with a smoother coma rich in volatile gas. The fourth reason is simple chance. Our instruments catch some objects at favorable angles and miss others that are equally abundant. When we place Oumuamua, Borisov, and 3I Atlas side by side, we are looking at a tiny sample drawn from a very broad distribution. The differences are not contradictions. They are the natural spread of stories in a large population. The next time we meet such a traveler, we should be ready with a modest ship designed to greet and to learn. The comet interceptor idea is a good seed for that plan. A waiting craft near the second Earth-Sun balance point can hold station for years with light propellant use. When a new visitor is announced, it can make a modest burn and place itself on a crossing path. Instruments should be chosen for answers that light does not give from afar. A visible and near-infrared imaging spectrometer to read water, carbon dioxide, carbon monoxide, and faint organic bands. an ultraviolet spectrograph to catch the hydrogen glow that comes from sunlight breaking water apart, and to read the fingerprints of carbon compounds, a thermal infrared camera to measure the warmth of the nucleus and to estimate size through its glow even when dust veils the shape, a polarimeter to weigh the porosity and shape of grains through the alignment of scattered light, a dust analyzer that sips grains and weighs their mass, their elemental ratios, and the structure of their fragments, a mass spectrometer for gas that can tell deuterium to hydrogen ratio in water, carbon-12 to carbon-13 ratios in carbon-bearing molecules, and nitrogen-15 ratios that speak to birth zones, a magnetometer and a plasma instrument to feel how the solar wind drapes around a new coma. 2 cameras, one narrow angle for close shapes and one wide angle for context, will paint the portrait. None of these instruments needs to be exotic. Together, they would turn a brief meeting into a deep lesson. As we describe such lessons for a broad audience, we can keep a gentle rule close at hand. Careful documentary work does not need to inflate. The truth is already astonishing. If a measured acceleration is small and consistent with gas flow, say so plainly. If a spectrum has a hint of a molecule at the threshold of detection, say that it is a hint and invite better data. If 2 teams disagree, tell the viewer why with kindness. Perhaps one team used a different calibration star. Perhaps another removed the coma differently. Show the method so that the result has a reason behind it. Replace the urge for a twist with the deeper pleasure of clarity. A bedtime documentary is especially well suited to this approach. Its task is to inform and to soothe, not to jolt. Uncertainty is not a flaw. It is a measure of what remains to learn. There are 3 companions that always walk with us. Statistical uncertainty is the spread that comes from counting few photons or from measuring under soft seeing. Systematic uncertainty is the bias that comes from instruments and methods. Model uncertainty is the gap between nature and our equations. The calm practice is to show all 3 as honestly as we can. Present a brightness as a band rather than a point. Plot a family of possible paths as a fan that narrows with new nights. Say that a molecule is detected at a certain confidence with a certain sensitivity limit. This vocabulary, far from dull, is the music of real knowledge. It tells the listener that what is known is held firmly, that what is suspected is held lightly, and that what is unknown is not feared. When we gather all the threads for 3I Atlas and ask whether its interstellar status stands on firm ground, we find a neat division between strong pillars and soft edges. The strong pillars are these. The path is cleanly open with a large excess speed that no plausible planetary flyby within the solar system can produce. The inbound direction and speed match the expectation for a visitor from outside rather than a rare object expelled from our own distant cloud. The appearance and the chemistry are those of a natural comet. The small extra accelerations are aligned with outgassing and sunlight pressure, not with any exotic force. The soft edges are these. The nucleus size and shape remain uncertain because the coma hides the core during the best windows. The rotation state is only lightly constrained because the light curve is mixed with activity. The ratios of gases are reported with wide bars because distance and geometry limit sensitivity. None of these soft edges undermine the pillars. They only mark the places where more data would sharpen the picture. After reading every study we could gather, what part of the portrait changed? We moved from a blank page with a moving dot to a gentle family likeness. The body behaves like a comet with gas and dust that follow the sun and build a modest tail. The chemistry leans toward common volatiles that leave fingerprints in the infrared and ultraviolet. The non-gravitational push is present at a level that fits ordinary outgassing. The orbit is secure and the closest approach to Earth is safe and far. The uncertainties are honest and shrinking. The priorities for the next season therefore become clear. Monitor brightness with disciplined cadence to separate rotation from activity. Secure spectra at times when the geometry favors gas lines that are otherwise masked by Earth's air. Measure polarization at several phase angles to fix grain structure. Continue the search for earlier precovery images to lengthen the arc. Coordinate large telescopes in both hemispheres to track the evolution through and after closest solar approach. Each of these tasks is simple to say and careful to do. All that remains is to step back and let the whole scene settle like dusk over quiet water. In the space of less than 1 human decade, we have greeted 3 travelers from other suns. Each brought a distinct accent. One was dry and strange. One was a familiar type of comet. And this new one speaks softly in the language of water and carbon dioxide with dust that fits what we know and deepens it. From a dust grain, we learned that distant disks mix hot and cold. From an open orbit, we learned again that ejection is a normal part of making planets. From a modest tail, we learned that sleep between stars does not destroy, it preserves. From the rhythm of careful studies, we learned that science moves well when it moves slowly and together. The truth about 3I Atlas is not a secret in a headline. It is the patient outline of a natural visitor written across many papers and many nights. It tells us that the solar system is not isolated. It is a clearing in a living forest. Objects drift in, objects drift out. When we are ready to meet them with open instruments and steady words, they will teach us more than we knew the night before. The last chapter in our quiet investigation looks forward. It asks which ships we will send, what instruments they will carry, and what truths they can gently lift from a passing traveler like 3I Atlas without disturbing its ancient sleep. First come the watchers, because discovery begins with open eyes. In the Chilean Andes, a new observatory is preparing to begin a decade-long movie of the sky. It will sweep the heavens every few nights with an immense digital camera and a mirror that drinks starlight deeply. This observatory will turn rare events into expected ones. Faint moving points that would once have slipped by will be pinned to a nightly record and announced. Within a year of full operations, it is expected to raise the rate of discovery for fast-moving visitors, including the occasional body from interstellar space, and it will do so with a cadence that transforms anecdotes into statistics. The same torrent of images will also help planetary defense by revealing dangerous objects that were previously hidden in sun glare. Above the atmosphere, another sentinel is nearing the starting line. A dedicated infrared telescope called Near-Earth Object Surveyor is planned to wait at the first Sun-Earth balance point, where it can look inward toward the hot glare that blinds ground-based instruments. Because it sees the gentle thermal glow of an object rather than its reflected sunlight, it can find dark bodies that would otherwise remain invisible. The The timetable states no earlier than the month of September in the year 2027 for launch, and the mission is designed to run for many years. Although its main charter is safety, its broad net will catch the unexpected. When a visitor arrives from interstellar space, an early and accurate detection from an infrared eye will lengthen the time we have to study, and perhaps even to plan a meeting. Waiting in deep space, there will soon be a patient craft made for exactly that meeting. The European Comet Interceptor will launch together with the Ariel mission and coast to the second Sun-Earth Lagrange point, where gravity balances in a quiet saddle. There it will sit for as long as several years, dozing with instruments warm and ready, listening for an alert about a fresh long-period comet or even a passing interstellar object. When the call comes, the craft will depart its post and aim for a one-time flyby. In the final approach, it will divide into 3 bodies that fly in formation. A main spacecraft will survey from a safe distance. 2 smaller probes named B1 and B2 will dive close to taste gas and dust where the coma is thick. This simple choreography lets one mission paint a 3-dimensional portrait of a primitive nucleus while measuring fields, plasma, and the shape of the bow where the solar wind meets a new atmosphere. The plan is to ride with Ariel in the year 2029 and then wait in quiet readiness. What can such a meeting reveal that a telescope on Earth cannot? The first treasure is composition without guesswork. Mass spectrometers that sip gas directly can weigh isotopes. The ratio of deuterium to hydrogen in water is a slow clock that tells where in a protoplanetary disk that ice likely formed. Carbon-12 to carbon-13 ratios and nitrogen-15 signatures extend that story. A dust analyzer can catch grains, weigh their size, and separate fragile clusters from compact shards. The difference between fluffy aggregates and glassy beads tells whether grains grew gently in cold fogs or were melted and cooled near a star. Polarimetric images can read the texture of coma dust by the way it aligns light. Cameras working in visible and infrared bands can map jets, fractures, and dark mantles on the nucleus, and can even measure temperature patterns that say how the surface stores heat. A second treasure is context. 3 craft measuring at 3 distances can reconstruct how gas and dust flow, where the flow begins, and how it changes with sunlight and rotation. A third treasure is the dance with the solar wind. Instruments that feel charged particles and magnetic fields can watch a new atmosphere breathe as it is draped by solar wind and as a bow shock forms. If an interstellar body is the target, these measurements will be our first in situ reading of a comet born under another sun. Comet Interceptor is not a heavy lifter. It is a careful visitor designed for a first handshake with minimal risk and maximum clarity. Engineers are also sketching a companion idea that moves from patience to pounce. A small spacecraft could wait in a loose orbit near the second Sun-Earth balance point, powered by efficient ion engines. The moment a suitable target appears, it can thrust gently but continuously to shape a crossing path. The same electric engines that give it patience also give it precision. This is not a fantasy. Studies show that targets like 3i Atlas can be reachable with energy requirements no worse than several ordinary missions within the solar system. The key is readiness. A craft must already be in space, already checked out, with a tank that holds months of electric propellant, and with software that can accept a new path on short notice. We will also continue to measure from afar with instruments that have grown quietly powerful. The James Webb Telescope has already shown that it can read faint molecular lines in comets within our own family. Given the right geometry and a well-timed target of opportunity, it can extend that skill to a visiting body and pull out signatures of water, carbon dioxide, and carbon monoxide, even through a soft coma. The European Euclid mission built for cosmology has already surprised astronomers with incidental moving object detections. It can contribute precision astrometry and high-quality images when the timing and the field align. Together with the patient ground-based movie from the Andes and the thermal eye of the infrared surveyor, a web of instruments forms around any new visitor. Each thread in that web plays to its strengths, while the others fill the gaps. There is a wider horizon that is worth mentioning, even if it does not aim at comets directly. A mission concept called Interstellar Probe studies the possibility of sending a craft past the boundary where the solar wind yields to the thin breath of the galaxy. Such a craft would not chase visitors. It would become a visitor itself, sampling the local interstellar medium far from the sheltering influence of our star. The technology to launch such a probe exists today, but the heat and radiation of a close solar flyby to gain speed would test materials greatly. Even at modest speeds by cosmic standards, such a mission would be a generational project. The reward would be a direct reading of the environment that drifting interstellar comets cross between stars. That context would make every future encounter richer. What might we discover in the next 10 or 20 years as these watchers and these travelers take their places? First, we are likely to find that interstellar comets are not rare. With a deep all-sky movie and an infrared eye in space, detections may arrive every few years and perhaps several times in a year if we are fortunate. We will begin to see families within the visitors. Some will be dusty and active like the comet discovered by Borisov. Some will be quiet shards like the first visitor named Oumuamua. Others will behave like Three-Eye Atlas, waking gently with water and carbon dioxide and carrying dust that looks familiar but not identical to our own. With each detection, the catalogue expands and the statistical picture sharpens. Second, we will measure with confidence the isotope ratios that anchor stories of origin. The deuterium to hydrogen ratio in water will show how far from a star that water froze. Ratios of carbon and nitrogen will map chemical neighborhoods in other disks. If noble gases can be detected in the coma, they will speak of the pressure and temperature at birth. This chemistry will allow us to compare the recipes of many kitchens where planets are baked. We will learn whether many systems mix hot and cold material as vigorously as our own, where crystals formed near the young sun are found today in comets that live far out in the cold. Third, we will see how dust is built. Some comets will exhale fragile clumps of submicron grains that break easily in sunlight. Others will deliver tougher aggregates with glassy shards. The difference matters. The sizes and strengths of grains set the way a disk cools and clumps, and whether it feeds small worlds or starves them. Grain structure also controls how sunlight pushes on the coma and tail, which in turn refines our orbit fits and our understanding of non-gravitational accelerations. Fourth, we will watch microphysics become gentle machinery. High-cadence imaging will let us see how jets turn on and off with local morning and afternoon on a spinning nucleus. Thermal mapping will show where blankets of dust insulate pockets of ice, and where fractures act as vents. Plasma instruments will record how a new atmosphere learns to wear the solar wind like a cloak. These are not loud discoveries. They are the soft skills of a field that values process over spectacle. Fifth, we will learn how to meet a stranger safely. A first success by a waiting interceptor will teach practical lessons about navigation in a dusty environment, about dividing into multiple probes for a brief three-body ballet, and about gathering data at high speed without overwhelming our storage or our downlink. Those lessons will be shared quickly. A second interceptor could carry a small penetrator to test crust strength, or a micro-free flyer to sample dust away from spacecraft fields. A third could experiment with new sails or new electric engines. Progress will not come in a rush. It will arrive as a series of calm steps that build on one another. Sixth, we will become better at telling the story in a way that fits the night. The healthiest documentaries will keep the temperature low and the curiosity high. They will show the data and the uncertainties side by side like two hands folded together. They will explain why two teams report different gas ratios by pointing out the difficulty of separating coma and nucleus, or the way Earth's air swallows certain infrared lines. They will avoid the easy excitement of sensational claims when the ordinary interpretation already fits. In doing so, they will build trust, and trust will make difficult ideas easier to carry into sleep. In the background of all this, the truth about risk will remain stable. The orbits of interstellar visitors usually keep them far from Earth. The energy that makes their paths open also makes close encounters unlikely. Planetary radar will seldom be able to reach them because the distance is large and the coma scatters the signal. Instead, we will rely on thermal measurements from space, precise positions from ground and orbit, and the patient compilation of light curves to reduce uncertainty. When rumors rise, the calm answer will be at hand. The path is safe, the distance is great, the danger is none. There is a final gift we can expect, and it is not a number, it is a feeling. Interstellar comets and their cousins remind us that our solar system is not a lonely island. It is a clearing in a forest with footpaths that lead in and out. Some paths bring guests, some see us off on our own journeys. With each visitor, we are offered a conversation with another place that we cannot yet reach. With each careful mission, we answer with a question and receive a small, precise reply. In the years ahead, the watchers will scan, the surveyor will glow in infrared, the interceptor will wait, and a few studies will argue loudly before the data softens them into harmony. From time to time, the galaxy will send a traveler near enough to greet. We will read its breath and weigh its grains and feel the touch of the solar wind on its new atmosphere. We will add a line to a table and a page to a book. Quietly, the picture of other planetary systems will gain color and depth until it feels as familiar as a map of our own coasts. Thank you for spending this time with a gentle mystery. As you close your eyes, imagine a small ship waiting in the darkness near the second Lagrange point. Instruments warm, solar panels steady, a patient heartbeat in the quiet. Imagine a message arriving that a new visitor is on the way. Picture the ship turning its face toward the faint moving point and beginning a slow, graceful burn. Somewhere far from any noise, the universe is already preparing the next conversation. Sleep well.